Right now, 24 satellites circling above your head are each drifting 38 microseconds off schedule every single day. That sounds negligible. It isn't. Without relativistic correction, your GPS would accumulate 10 kilometers of position error daily. By next Tuesday, it would route you into a lake. The reason those clocks drift isn't a hardware flaw, it is gravity bending time itself. Clocks in weaker gravity, higher up, run faster than the one in your pocket. Newton gave us the equation for gravity's strength in 1687 and called it done. What he never answered, what took 228 more years to crack, is what gravity actually is. Not how strong, not what it does, what it is. Einstein's answer: there is no force. There is only the shape of space-time, bent by mass. And most of that bending near Earth is not space at all. It is time. The rubber sheet you are taught to picture is missing half the story. Today, we build the complete one. Consider what that drift really means. The clock in your pocket and the clocks aboard those satellites were built identical, set ticking in perfect agreement. Then we lifted one set of them roughly 20,000 kilometers into the sky, and they began to disagree. Not because the engineering failed, not because the hardware aged, but because the two clocks now rest at different depths of gravity, and gravity, it turns out, sets the rate at which time itself flows. Higher up, where Earth's pull is gentler, time runs a little faster. Down here, closer to all that mass, it runs a little slower. The gap is far too small for your senses to feel. It is not too small for the universe to enforce. Each day, the satellite clocks gain about 45 microseconds, simply because they sit higher in Earth's gravity. Their enormous orbital speed claws some of that back, slowing them by roughly 7 microseconds. What remains is a net 38 microseconds of disagreement, accumulating quietly, day after day after day. Left uncorrected, that error swells into kilometers within hours and into tens of kilometers within a single day. The most ordinary act imaginable, asking a glowing rectangle where you are standing, depends entirely on engineers having accepted one of the strangest ideas a human mind has ever produced. Time is not the same everywhere. Time bends. There is a single sentence that holds the whole of this idea, written by the physicist John Archibald Wheeler. Matter tells space-time how to curve, and curved space-time tells matter how to move. Read it once and it sounds elegant. Read it again, and a question opens beneath it like a trapdoor. Why should matter tell space-time anything at all? Why should the empty distance between the stars possess a shape that can be bent? And why, of everything that might bend near a world like ours, is it mostly time, and so little of it space? Here is what will quietly dismantle everything you are taught about how the world holds itself together. Gravity is not a force reaching across the void to tug at distant things. Nothing is pulling on the moon. Nothing is pulling on you. There is only geometry, the unseen contour of space and time, and every falling object is simply tracing the straightest path available through a landscape that mass has curved. The apple does not drop because the earth hauls it downward. The apple drops because the earth has bent the very stage on which the apple's small story unfolds. If you find that idea as quietly astonishing as it truly is, do me one small kindness and tap the like button and think about subscribing. It genuinely helps this channel grow, and it lets me keep making these long, slow journeys through the deep structure of reality for you. There is nothing here to solve, and nothing you need to keep pace with. So dim the lights. Rest your head against something soft. Let your breathing slow to the rhythm of these words. Make yourself warm and comfortable. We have 228 years of mystery to walk through, gently, one careful step at a time, with a single beautiful equation waiting quietly at the end of the road. Let's begin. To understand why such a strange and beautiful idea took so long to arrive, we have to walk back to the man who first gave gravity its rules. The year is 1687. In Cambridge, England, A reclusive and famously difficult mathematician named Isaac Newton publishes a book whose long Latin title is almost always shortened to a single word: the Principia. It is, by nearly any honest measure, the most consequential scientific book ever written, and inside it lives a single law of universal gravitation, an equation so quietly powerful that it describes the fall of an apple and the sweep of the moon across the night sky using the very same handful of symbols. One rule, two utterly different worlds, the same hidden machinery underneath both. Consider what that actually meant to the people who first read it. For the whole of human history before that moment, the heavens and the earth had been treated as two separate kingdoms, governed by two separate sets of laws. The ground was the realm of falling and breaking and decay. The sky was the realm of perfect circles and eternal lights that never fell at all. Newton erased that ancient border in a few pages of mathematics. He showed that the same force which pulls a dropped stone toward the dirt is the very same force that holds the moon in its long, patient circle around us. Not a similar force, not a cousin of that force. The identical thing, scaled across 250,000 miles of empty space. The power of this was almost difficult to believe. With Newton's law in hand, astronomers could do something that had never been possible before. They could predict. They could point their instruments at a patch of empty sky and say, with calm confidence, that a particular point of light would be in a particular place on a particular night, years from now. And then they could wait, and watch, and be proven right. The tides rose and fell in obedience to the equation. The planets traced their paths exactly where the numbers said they should. Across the 18th century, the law of gravitation became the crown jewel of human reason, the single clearest piece of evidence that the universe was not chaos but clockwork, and that the clockwork could be read by anyone patient enough to learn the language. And yet, buried inside that triumph was a question that Newton himself could not answer, and the strange thing is that he knew it. His equation told you exactly how strong gravity was. It told you that the pull weakened with the square of the distance, that doubling the gap between two objects cut their attraction to 1/4 of its former strength. It gave you the how much with breathtaking precision. But it said nothing whatsoever about the how. It never once explained what gravity actually was, or by what means the sun could reach across 93 million miles of absolute nothing and hold the earth in its grip. There was no rope. There was no rod. There was no visible thread of any kind connecting the two bodies. There was only empty space, and somehow, across that emptiness, the pull arrived instantly and without explanation. Newton called this problem action at a distance, and he was deeply, privately uncomfortable with it. He wrote in effect that the idea of one body acting upon another across a vacuum, with no intervening substance to carry the force, was so absurd that no thinking person could ever truly accept it. He had given the world the rules of gravity, while openly confessing that he did not understand the reason for them. This was not a small footnote. This was the deepest crack at the foundation of the most successful theory in the history of science. The equation worked perfectly, and no one could say why it worked at all. That crack did not close. It widened in silence for 228 years. Generation after generation of physicists used Newton's law every single day, built bridges and predicted eclipses and charted the courses of comets with it, and simply learned to look past the hole at its center. The mystery was not that the math was wrong. The math was astonishingly right. The mystery was that nobody knew what the math was describing. Gravity was a perfectly reliable ghost. You could measure its weight, predict its motions, trust your life to its constancy, and never once catch a glimpse of its face. Here is what makes that gap so haunting in hindsight. The very perfection of Newton's equation was the thing that hid the answer. Because the law fit the observations so well, almost everywhere, almost all the time, there was no obvious pressure to dig deeper. When a theory predicts the sky correctly to the limit of your instruments, you do not go looking for a replacement. You celebrate. And so the question of what gravity truly is became a kind of philosophical luxury, a puzzle for late-night conversation, rather than an urgent problem demanding a solution. The universe was keeping its secret not by hiding it, but by behaving too well to provoke the question. But the universe, it turns out, had left a single loose thread hanging in plain sight, and it was waiting on the smallest, fastest, most overlooked planet in the entire solar system. To find that thread, we have to leave Newton's century behind and move forward to the year 1859. The place is the Paris Observatory. The man is a brilliant and notoriously prickly French astronomer named Urbain Le Verrier, one of the most gifted calculators of his age, a person who could wring predictions out of Newton's equations with a precision that bordered on the supernatural. And Le Verrier had turned his enormous attention toward the planet Mercury. Mercury is a difficult subject. It hugs the Sun closely, racing around it in a tight, swift, lopsided orbit, forever lost in the solar glare, and visible from Earth only in brief windows at dawn or dusk. Its orbit is not a perfect circle, but a stretched ellipse, and that ellipse does something that all orbits do to some small degree. It slowly rotates. The entire oval shape of Mercury's path turns very gradually around the Sun, so that the point of the planet's closest approach creeps forward a little more with every pass. This slow turning is called precession, and Newton's law predicted it beautifully, because the gentle tugs of all the other planets nudge Mercury's orbit along by a calculable amount. So Le Verrier did what he did best. He took the gravitational influence of every known planet, Venus pulling from one side, Earth and Jupiter and all the rest adding their distant contributions, and he summed it all together with painstaking care. Newton's mathematics predicted that Mercury's orbit should precess by a total of 531 arcseconds per century. To understand how fine a measurement that is, you have to know that an arcsecond is an almost absurdly small angle. There are 3,600 arcseconds in a single degree, and 360 degrees in a full circle. A single arcsecond is roughly the width of a small coin seen from 2.5 miles away. Le Verrier was predicting a drift measured in slivers of a degree, accumulated across an entire century. And here the loose thread finally pulled taut. When astronomers measured the real precession of Mercury's orbit, the number that came back was not 531 arcseconds per century. It was 574. The planet was turning faster than Newton's flawless law allowed, and the difference between prediction and reality was a stubborn, persistent, unexplained 43 arcseconds per century. Not a rounding error, not a smudge in the data that better telescopes would wipe away. A real, measured, repeatable gap between what the most successful theory in science demanded and what the sky actually did. Now 43 arcseconds per century sounds like nothing at all. It is nothing, very nearly. It is so small that over an entire human lifetime, the discrepancy would amount to a hair's width of extra turning. An error so tiny that most physical theories would never even notice it, let alone be threatened by it. But Newton's gravity was not most theories. It was the theory that predicted eclipses to the minute and guided ships across oceans, and had never, in nearly 2 centuries, been caught in a clear and unexplainable mistake. For a law that exact, 43 arcseconds was not a footnote. It was a scream. It was the universe saying, very quietly and very precisely, that something at the foundation was not quite right. Le Verrier, being a man of his time and a devoted Newtonian, did not conclude that the law itself was broken. He reached for the same explanation that had served him brilliantly once before, when an unexplained wobble in another planet's orbit had led him to predict, correctly, the existence of an unseen world. He proposed that there must be a hidden planet, closer to the Sun than Mercury, a small dark body whose gravity was nudging Mercury along that extra 43 arcseconds. He even gave this imagined world a name. Astronomers searched for it for decades. They scanned the blinding region near the Sun again and again, certain that the missing planet was hiding somewhere in the glare. They never found it, because it was never there. This is the quiet beginning of the end for action at a distance. The 43 arc-seconds would not go away, and no hidden planet would account for it, and no clever adjustment to Newton's beloved equation could absorb it without breaking something else. For more than 50 years this single, tiny number sat at the heart of physics like a splinter that could not be removed. A crack in the most trusted theory humanity had ever produced, visible to anyone who cared to look and explicable by no one. The greatest minds of the 19th century stared at it and had no answer. The splinter would wait, patient and unmoving, for a young man who had not yet learned to see space and time as anything other than the empty stage on which the planets danced. Before we can understand how one young man would finally pull that splinter free, we have to confront the way nearly all of us are first taught to picture gravity in the first place. There is a single image that almost everyone meets at some point, in a classroom or a documentary or a quiet diagram in a library book. It is worth pausing on, because it is at once the most helpful picture ever invented and the most quietly misleading. Imagine a large rubber sheet, stretched flat and pulled taut at its edges, like the surface of a trampoline. Now set a heavy bowling ball down in the center. The sheet sags. It dips into a smooth, curved well, deepest beneath the ball and shallowing as it spreads outward toward the rim. Roll a small marble across that sheet, and the marble no longer travels in a straight line. It curves. It spirals inward toward the heavy ball, circling faster and faster, like water turning down a drain. Nothing reaches out and seizes the marble. There is no rope, no magnet, no invisible hand. The marble simply follows the shape of the surface beneath it, and the bowling ball has bent that surface into a slope. This is the rubber sheet, and for a first encounter it is almost perfect. It captures the single most important idea anyone would ever have about gravity. The pull between worlds might not be a force at all, but a shape that objects are quietly following. The marble is not dragged toward the ball, the marble is falling along a curve. Once you have watched it spiral inward, you can never quite look at the moon circling the Earth, or the Earth circling the Sun, in the same innocent way again. They are not tied to anything. They are rolling along the curved floor of a valley they cannot see. But here is where the beautiful picture begins to lie to you. Not in some small footnote that only a specialist would ever notice. In the very heart of the thing. The rubber sheet shows you space bending. It shows a flat surface sagging downward into a third dimension, a two-dimensional world drooping into depth. From that image, almost everyone walks away believing that gravity simply is the bending of space, and that when you stand upon the Earth, what holds you to the ground is space itself, curved beneath your shoes like the slope of that well. This is not true, not entirely false, but false about precisely the part that matters most. Near the surface of the Earth, the curving of space contributes almost nothing to the weight you feel. The force that pins you to your chair, that pulls a dropped cup to the floor, that holds the oceans pressed against the planet, comes not from the warping of space. It comes from the warping of time. This is the part the rubber sheet can never show you, because the rubber sheet has no clock. It has only width and length and the depth it sinks into. It has no way to draw the fourth dimension, the dimension of time, and so it simply leaves time out of the picture entirely. In leaving time out, it hides the single most important fact about how gravity truly works near a world like ours. Time does not flow at the same rate everywhere. It runs very slightly slower where gravity is stronger, nearer to a great mass, and very slightly faster where gravity is weaker, farther away in the open. A clock resting on the floor ticks more slowly than a clock sitting on a high shelf in the same room. The difference is almost unimaginably small. It is real, it has been measured in laboratories, and it is the quiet engine of your weight. Consider what this means. Every person who has ever lived has aged, by the very smallest margin, faster at the top of a staircase than at the bottom of it. Stand for a lifetime with your head a little higher than your feet, and your head will have drifted a sliver further into the future than your feet have. The amount is so tiny that no human sense could ever register it, far smaller than a single blink spread across an entire life. Yet it is not zero. It is the same effect, scaled down almost to nothing, that holds you against the ground with a pull you have felt every second since the day you were born. If you could somehow stand at a place where time ran perfectly evenly in every direction, with no slope to its flow at all, you would feel no weight whatsoever. You would drift, weightless. Not because gravity had been switched off, but because there would be no faster, no slower for anything to fall toward. An object drifting freely, with nothing pushing or pulling on it, does something strange inside this uneven river of time. It drifts toward the region where time runs slower. It falls, in other words, not because space is tilted beneath it, but because the future itself is arriving at different speeds in different places, and the natural path of any object is to bend gently toward the slower clock. Gravity, here on the surface of the Earth, is very nearly all of this. It is the warping of time, wearing the simple costume of a falling stone. The rubber sheet, for all its elegance, shows you the costume and hides the actor. And so we arrive back at the splinter, back at the 43 arcseconds of Mercury, at the silent gap that stretched for more than 2 centuries between the man who wrote down gravity's rules and the man who had finally explained them. For 228 years, beginning with the publication of the Principia in 1687, humanity held a law of gravity that worked. It worked magnificently. It steered ships across blank oceans, predicted eclipses to the minute, and led astronomers to planets no eye had ever glimpsed before the mathematics promised they were there. In all that time, across all those generations of formidable minds, not one person could say what gravity actually was. Newton himself had refused even to guess. His law told you exactly how strong the pull between two objects would be. It told you nothing whatsoever about why that pull existed. For nearly a century after Newton, the picture of the rubber sheet did not even exist, because the idea behind it did not exist. Thinkers were taught instead to imagine gravity as a kind of invisible cord running between every pair of objects in the universe, an unseen tension stretched across the void, drawing the Earth toward the sun and the apple toward the ground. It was a deeply uncomfortable idea, and the most honest among them knew it. A cord between the Earth and the sun would have to span an emptiness so vast that light itself needs minutes to cross it, attached to nothing, transmitting its pull across the gulf. Newton had handed the world a law that worked and an explanation that satisfied no one, least of all himself. For more than 2 centuries the discomfort simply sat there, unexamined, because nothing better had ever been offered to take its place. The answer was waiting. It was not a stronger force, and it was not a sharper equation, and it was not a hidden planet circling unseen in the sun's glare. The answer was stranger than any of those, and far harder to accept. The answer was that there was no force at all. Everything that generations of physicists had quietly assumed to be the empty stage, the blank and changeless backdrop against which stars and planets played out their motions, was itself the actor in the drama. The stage was bending. The stage was stretching. The stage was slowing time near every massive thing in the cosmos. And that bending, stretching, slowing fabric was the whole of gravity, and no one had yet dared to imagine it. No one, that is, until a single mind performed an experiment that needed no laboratory and no instrument of any kind. It required only a chair, a quiet afternoon, and the willingness to take an ordinary thought seriously. In the years around 1907, a young man working at a patent office let his attention wander toward a question that sounds almost too simple to matter. What would a person actually feel if the floor beneath them gave way and they began to fall? Not what would happen to them. What would they feel? The answer, he realized, was nothing. A person in free fall feels no weight at all. Drop a coin from your pocket as you fall, and it does not race toward the ground ahead of you, because you and the coin are falling together, side by side, at exactly the same rate. To you, the coin simply hangs in the air before your eyes. Your stomach lifts. Your body presses against nothing. For those few seconds, gravity has not vanished, and yet every sensation of gravity has disappeared completely. This was the seed of everything that followed, and it was the strangest idea the young man had ever had. He turned the thought inside out and built it into a sealed box. Imagine a windowless elevator, far out in empty space, with a single person standing inside it. Imagine that some great cable begins to haul that elevator upward, faster and faster, accelerating at 9.8 meters per second, every single second. That precise rate is not chosen at random. It is the exact rate at which objects accelerate when they fall toward the surface of the Earth. Now ask the person inside the box a simple question. Where are you? They cannot answer. They feel their feet pressed firmly against the floor. They feel the familiar weight settling into their shoulders and their spine. Drop a ball, and it falls to the floor at a comfortable, recognizable pace. Every sensation tells them they are standing in a room on Earth, held down by gravity, exactly as you are held down in your seat right now. And every one of those sensations is a lie, or rather it is the truth twice over, because the box is not on Earth at all. The box is being dragged through empty space by a cable, and the person inside has no way, none whatsoever, to tell the difference. This is the heart of what came to be called the equivalence principle, and it is one of the most quietly devastating ideas in the history of human thought. There is no local experiment, no measurement of any kind that can be performed inside that sealed room that could distinguish the pull of gravity from the push of pure acceleration. You could weigh objects. You could swing pendulums. You could drop feathers and hammers and watch them fall. Every result would come back identical in both cases. Not approximately identical. Not close enough for practical purposes. Identical in principle, down to the finest measurement physics will ever permit. Sit with what that means, because it is easy to let it slide past. If gravity and acceleration cannot be told apart by any experiment, then in some deep and inescapable sense, they are not two different things at all. They are one thing wearing two costumes. And acceleration is not a force that lives inside objects. Acceleration is geometry. It is a description of how a path bends through space and through time, which means that gravity, the most familiar force in all of human experience, the thing that holds your cup to the table and your feet to the floor, might not be a force in any meaningful sense whatsoever. This was the crack through which an entirely new universe poured in. For more than 200 years, every physicist had pictured gravity as a pull, a rope of invisible influence stretching between masses, hauling them toward one another across the empty dark. The young man at the patent office had just shown that the rope might not exist. Not because the pull was too weak to detect, not because the rope was woven from some undiscovered substance, but because there was nothing there to do any pulling. The falling person feels no force, because there is no force. There is only the shape of the space they are falling through. It took him most of a decade to turn that single afternoon's insight into mathematics, and the work very nearly broke him. He wrestled with geometry that few mathematicians of his era fully understood. He filled notebooks with equations that collapsed under their own contradictions. He made errors, corrected them, made new errors, and pressed on through years of frustration that aged him visibly. And then, on the 25th of November, 1915, Albert Einstein presented the finished theory in its complete and corrected form. He called it general relativity, and at its center sat a claim so radical that it took the rest of the scientific world years to absorb it. Gravity, Einstein said, is not a force. Gravity is the curvature of space-time itself, produced by the presence of mass and energy. A massive object does not reach out and grab the things around it. It bends the space and the time in its own neighborhood, and everything nearby simply follows the contours of that bending. The Earth does not pull the Moon. The Earth dimples the space-time around it, and the Moon, finding no flat path to follow, curves along the slope. The Sun does not tug on the planets across the vast emptiness that separates them. The Sun warps the geometry of its entire region of the cosmos, and the planets roll along the valleys of that warp like marbles circling a drain that never quite swallows them. Decades later, The physicist John Archibald Wheeler compressed the whole of this theory into a single sentence, and it remains the cleanest summary anyone has ever managed. Matter tells space-time how to curve, and curved space-time tells matter how to move. Read it slowly, because every word is load-bearing. It describes not a one-way command, but a conversation, a mutual and unending exchange written directly into Einstein's field equations. Mass shapes the geometry then steers the mass moves, and as it moves it reshapes the geometry again, and the geometry steers it anew, around and around, forever, in a feedback loop that has been running since the first instant of the universe. This is the answer that had been waiting on the far side of Newton's discomfort, and notice how completely it dissolves the old problem, rather than merely solving it. Newton had agonized over how gravity could reach across empty space to seize a distant world. Einstein's answer was that gravity never reaches across anything, because the space between the worlds is not empty in the way Newton had imagined. It is not a void. It is not a backdrop. It is a physical thing with a shape, and that shape is the gravity. There is no message that has to travel from the sun to the earth. The earth is already sitting inside the sun's curvature, the way a ball resting in a bowl is already inside the bowl's slope, needing no instruction to roll. And here is the detail that overturns the most basic intuition you carry in your body. When the moon circles the earth, or the earth circles the sun, you naturally picture an object being bent away from the straight line it would otherwise travel. You imagine the planet wanting to fly off in a straight path, and gravity yanking it back into a curve. Einstein's geometry says the opposite. The orbiting body is not being bent away from a straight line. It is following the straightest possible path available to it. The straight line itself has been curved, because the space-time it runs through has been curved, and a straight path through curved space is a curve. The planet is not resisting its natural motion. The planet is obeying it perfectly. Gravity is what straight looks like when the ground beneath the line has been bent. Consider what this asks of you. Everything you have ever been taught to call falling, you must now learn to call something closer to coasting. The apple does not fall because a force seizes it. The apple is released, and with nothing holding it in place, it begins to follow the natural geometry of the space-time around the Earth, a geometry that happens to point straight down toward the planet's center. You, sitting in your chair, are the one being interfered with. The floor beneath you is constantly pushing you off the free and straight path you would otherwise take. That pressure you feel in your seat right now, the solid, reassuring weight of your own body, is not gravity holding you down. It is the chair holding you up, shoving you away from the path that the curvature of space-time is forever inviting you to take. This is the equivalence principle, and it is the seed from which everything else grows. Picture the sealed elevator again, the one with no windows, the one Einstein imagined in order to trap himself inside a single impossible question. You are floating in deep space, far from any planet, far from any star, and the elevator begins to accelerate. The floor rushes up to meet your feet at 9.8 meters per second squared, and suddenly you have weight again. Your arms hang, a dropped coin falls, and here is the unsettling part. There is no measurement you can make, no experiment you can run inside that sealed box that could ever tell you whether you are accelerating through empty space or simply standing still on the surface of the Earth. Not a clever measurement, not a difficult one. There is no measurement at all, because the two situations are not merely similar, they are, in every way the universe allows you to test, the same thing. Sit with that for a moment. The pressure of acceleration and the pull of gravity are not two phenomena that happen to feel alike. They are one phenomenon wearing two names, and if they are truly indistinguishable, then everything we once believed about gravity as a force begins to dissolve. A force is something that reaches out and grabs. A force has a source and a target, and a line of action between them. But acceleration is not a grab. Acceleration is geometry. It is the shape of a path through space and time. So if gravity cannot be told apart from acceleration, then gravity too must be geometry. Not a hand reaching across the void to seize the falling apple. A landscape, invisible and everywhere, whose slopes and valleys decide which way is straight. It took Einstein the better part of a decade to turn that single insight into mathematics. The thought experiment came easily. The equations did not. He wrestled with the geometry of curved surfaces, with the strange new tools that described how distances stretch and angles bend when space itself is no longer flat. And on the 25th of November, 1915, he presented the finished form of the theory, a set of field equations that describe, with terrible precision, exactly how mass and energy bend the fabric of space-time, and exactly how that bent fabric then tells everything within it how to move. The 228-year silence that had begun with Newton ended in a single page of symbols. The question that had no answer finally had one. Decades later, the physicist John Archibald Wheeler distilled the whole of it into a single sentence, and it remains the most elegant summary ever written. Matter tells space-time how to curve, and curved space-time tells matter how to move. Read it slowly. There is no force in that sentence. There is no pulling, no reaching, no action across a distance. There is only a conversation, endless and mutual, between the things that have mass and the geometry they are embedded in. The Earth does not yank the Moon. The Earth tells the space-time around it how to bend, and the Moon, finding itself in that bent geometry, simply travels the straightest path available to it. That path happens to be a circle. We have been calling that obedience a force for 300 years, and the theory did something Newton's never could. It explained Mercury. Remember that stubborn anomaly, the 43 arcseconds per century that no one could account for, the tiny extra rotation of Mercury's orbit that had defied every correction for 56 years. Newton's law predicted the planet's orbit should precess by 531 arcseconds each century. The heavens insisted on 574. That missing 43 arcseconds was small enough to seem like an error and persistent enough to prove it was not. When Einstein took his new field equations and applied them to the warped spacetime near the Sun, the curvature of geometry produced exactly 43 additional arcseconds per century. Not approximately, not within a reasonable margin. Exactly. The crack that had run through the foundation of physics for over half a century was sealed, and it was sealed not by adding a new planet or a new force, but by changing what gravity fundamentally is. Consider what this means. The same idea that says you are coasting rather than falling, the same idea that says your chair is the only thing interfering with your natural motion, also predicts the precise wobble of a planet 50 million miles away. One geometry. One set of equations, from the weight in your seat to the orbit of the innermost world, all of it the same curved fabric, all of it the same straightest possible path bending around the mass of things. Which brings us, finally, back to the rubber sheet. You have seen the picture 1,000 times. A heavy ball pressed into a stretched elastic surface, marbles spiraling inward toward the dimple it makes. It is a useful image, and it is also a profoundly misleading one. Here is the problem. The rubber sheet shows you space bending, the flat surface dipping into a third dimension below, but it shows you only space. It says nothing about time, and near the surface of the Earth, the truth is almost exactly backward from what the sheet implies. The gravity that holds you in your chair, that pulls the apple to the ground, arises overwhelmingly not from the warping of space, but from the warping of time. The dimension the rubber sheet cannot draw is the dimension that matters most. This is the hardest thing in all of it to feel in your body, so let it arrive slowly. Time runs at different rates at different heights. It runs measurably slower near the ground than near the ceiling, slower at your feet than at your head, slower wherever the curvature of space-time is steeper. And matter, when it is free to move, drifts toward where time runs slow. The apple falls because the future, in the direction of the Earth's center, is unfolding just slightly more slowly than the future above it, and the apple, following its straight path through space-time, leans into that slowness. You are not being pulled down through space, you are being carried forward through time, and the geometry of that time is tilted toward the planet beneath you. The rubber sheet hides all of this. It invites you to imagine space-time as a passive stage, a flat backdrop that mass happens to deform, a surface that sits there waiting. But space-time is not a stage. It is not background. It is not a fixed and empty container in which events occur. It is a physical thing, as real as matter itself, and it bends and stretches and ripples and responds. It is an active participant in every event that has ever happened to you. The ground holds you up against it at this very moment. Every step you take is a negotiation with its shape. So when you next see that bowling ball on its stretched elastic sheet, remember what the picture leaves out. It leaves out the most important dimension. It leaves out time, and it leaves out the strangest truth of all, the one Einstein's equations whisper beneath every calculation, that the planet beneath you and the body you are sitting in are not separate from the geometry of the universe. They are written into it. The Earth curves the space-time around it, and that curved space-time reaches up through the soles of your feet and the base of your spine, and presses on you with the weight you have spent your whole life mistaking for a force. For 3 centuries, humanity believed gravity was something objects did to one another across the emptiness between them. It is not. There is no emptiness. The space between the Earth and the Moon, between your hand and the floor, between one star and the next, is not nothing. It is a fabric, and it has a shape, and that shape is bent by everything that exists within it. The question that opened this journey, the simple childlike question of why gravity should bend space at all, has begun to answer itself. Gravity does not bend space. Gravity is the bending. The 2 words describe the same single thing. And if that geometry is real, if space-time truly curves and tilts and slows in the presence of mass, then it should be possible to see it, not to feel it, the way you feel your weight, not to calculate it, the way Einstein calculated Mercury, to see it, directly, with instruments and photographs and human eyes, to catch the universe in the act of bending. And there was one moment, one rare alignment of sun and moon, and a remote island off the coast of Africa, when humanity tried to do exactly that. To see the bending of space-time, you must look at light. Light is the one thing in the universe that follows the geometry without argument. It carries no engines, no stubborn momentum of its own, no orbit it is trying to keep. Light simply travels wherever the road travels, and if the road itself is curved, then the light has no choice but to curve along with it. This was the quiet, devastating prediction buried inside Einstein's equations. A ray of starlight passing close to the surface of the sun should not move in a perfectly straight line. It should bend, ever so slightly, as it crossed the warped region of space-time that the sun's enormous mass had carved into being. The amount was almost nothing, a whisper of an angle. But it was a number, and a number can be measured, and a measurement is the only thing that separates a beautiful idea from a true one. Here is the problem. The stars whose light skims the very edge of the sun are, by their nature, almost directly behind the sun as we look out at them. And the sun is overwhelmingly, violently bright. You cannot photograph a faint star sitting beside the sun any more than you could photograph a single candle held against the face of a searchlight. The glare swallows everything. For the whole of human history, this simple fact made the experiment impossible. The exact stars you needed to study were drowned in the light of the very object you were trying to study them against. It was a cruel arrangement. The evidence existed, and the evidence was hidden, and it was hidden by the same thing that produced it. There was only one circumstance in all of nature that could solve this. Only one event capable of silencing the sun without destroying the sky around it. A total solar eclipse. When the moon slides into perfect alignment and covers the bright disk of the sun completely, the blinding glare vanishes for a few short minutes. The sky goes dark in the middle of the day, And in that sudden artificial twilight, the stars that sit close to the sun's hidden edge become briefly, gloriously visible. The moon does not merely darken the sky, it uncovers a hidden laboratory that exists for only a handful of minutes at a time, in only a handful of places on Earth, and only when the geometry of three bodies happens to agree. So the test took shape. Photograph those stars during a total eclipse, when their light grazes the sun on its way to us. Then photograph the very same stars months later, at night, when the sun is on the far side of the sky and their light travels to us through undisturbed space. Lay the two photographs side by side. If the positions match exactly, then light travels in straight lines and gravity has no hold on it at all. But if the stars near the eclipsed sun appear nudged outward, shifted slightly away from the place they occupy in the dark of an ordinary night, then their light has been bent, and the size of that shift would reveal which version of reality was true. Because there was not one prediction on the table, there were three. The first possibility was the simplest: 0. Light has no mass, and in the old way of thinking, gravity acts upon mass. So perhaps starlight would sail past the sun entirely untouched, bending not at all. The second possibility came from Newton's framework stretched to its limit, treating light as though it were a stream of tiny particles falling through the sun's gravity. That calculation gave a deflection of 0.875 arcseconds. An arcsecond is a unit so small it nearly defies imagination. It is 1/3600th of a single degree. If you held a coin at arm's length, the angle it covers in your vision is enormous compared to an arcsecond. The Newtonian shift was a fraction of even that tiny sliver, and the third possibility, Einstein's possibility, was exactly twice the Newtonian value, 1.75 arcseconds. Not a little more than Newton, precisely double, because Einstein's spacetime curves not only the path of the light through space, but the flow of time alongside it, and the two effects add together into a deflection twice as large as gravity alone could ever produce. Consider what this means. The difference between the three answers was the difference between three entire pictures of the universe. 0 meant gravity could not touch light, and the cosmos was simpler than Einstein dreamed. 0.875 meant Newton still reigned. His 200-year-old framework merely extended to a new kind of falling object. 1.75 meant that space and time were a single woven fabric, that mass bent that fabric, and that the bending was real enough to deflect a beam of starlight that had crossed the galaxy untouched until the final moment it passed the sun. The gap between Newton's answer and Einstein's answer was less than a single arcsecond. The fate of an entire conception of reality balanced on a sliver of an angle thinner than a hair seen across a room. And there was a complication, a private one, known only to Einstein and a few others. Einstein had been wrong once already, not about the existence of the bending, but about its size. In 1911, 4 years before his theory was finished, he had published a paper predicting that starlight would bend as it passed the sun. But that early calculation, made before he had grasped the full geometry of curved time, gave a deflection of only 0.83 arcseconds, almost exactly Newton's value. Had anyone tested it then and measured the bending accurately, they would have proven Einstein wrong, or rather, proven the incomplete Einstein wrong. It was only when he corrected and completed his field equations in 1915 that the number doubled to 1.75 arcseconds. Einstein knew this. He knew his earlier self had made an error. He carried the quiet knowledge that the universe had nearly caught him in a mistake, and that the corrected number was now the only thing standing between his life's work and its collapse. This is the strange honesty at the center of the whole affair. The man had publicly committed to a precise figure that could be measured against the sky. Not a vague claim, not a philosophical flourish, a number with decimals. That nature would either confirm or refuse. If the eclipse photographs showed 0, he was finished. If they showed Newton's smaller value, he was finished. and his own discarded paper from 1911 would have been closer to the truth than his masterwork. Only the doubled value, the 1.75, would vindicate him. A theory this bold does not earn the right to be believed because it is elegant. It earns that right only by surviving contact with the real, by predicting a thing in advance and then watching the thing arrive. The eclipse that would settle it was scheduled by the clockwork of the heavens for the 29th of May, 1919. It was, by a fortunate accident of celestial timing, an unusually long total eclipse, with the sun positioned against a rich field of bright stars known as the Hyades. More stars in view meant more measurements, and more measurements meant a sharper answer. But the path of totality, the narrow strip of Earth where the moon would fully cover the sun, fell across the Atlantic Ocean and the remote tropics. To stand inside that shadow, an observer would have to travel thousands of miles from the laboratories of Europe to places where the equipment had never been tested, where the weather could not be promised, and where a single afternoon of cloud could erase years of preparation in an instant. The man who carried that risk was the British astronomer Arthur Stanley Eddington. He was among the very few people outside Germany who had read Einstein's work carefully, understood it deeply, and believed it might be true. There was a bitter irony in this. The First World War had only just ended, and Einstein was a German, working in Berlin, an enemy of the British state by the cold logic of nationality. Yet here was an Englishman preparing to sail to the edge of the world to test, and perhaps to confirm, the theory of a man his country had been at war with months earlier. Eddington did not see an enemy's theory. He saw a question the universe could answer, and he intended to ask it. The plan split into two. Eddington himself would travel to Principe Island, a small volcanic island off the western coast of Africa, hauling delicate telescopes and photographic plates across the ocean to a place where the eclipse would be total. A second team, led by Andrew Crommelin and Charles Davidson, would sail in the opposite direction, to Sobral, in northern Brazil, to observe the same eclipse from across the Atlantic. Two stations, two continents, two independent attempts to photograph the same shifted stars. If one site failed, the other might succeed. If both succeeded, their agreement would be impossible to dismiss as accident or error. The geometry of the universe was about to be cross-examined by two witnesses, standing on opposite shores of the same ocean, looking up at the same darkened sun. And so the instruments were crated and loaded, and the ships left their harbours, carrying glass and brass and the weight of a question that had waited 228 years for an answer. Eddington was not sailing to feel gravity. Every person who has ever lived has felt gravity. He was sailing to see it, to catch it in the act of bending the path of light itself, to photograph the curvature of space-time, and develop it on a glass plate he could hold in his hand. The theory had made its promise. It had named its number. Now the only thing left was the sky, and the moon, and a few short minutes of darkness in the middle of an African afternoon, when the universe would either keep Einstein's promise or break it. The eclipse came on the 29th of May, 1919. On Principe Island that morning, the sky refused to cooperate. A tropical storm had crossed the island in the hours before dawn, and rain still fell in heavy sheets across the small clearing where Eddington had assembled his telescope. He could not see the sun. He could see nothing but grey. Totality was coming whether the weather permitted it or not, and the weather did not seem to care that the most important measurement of the century depended on a few clear minutes. Then, in the final moments before the moon's shadow swept in, the clouds began to thin. Not to clear, not to open, but to thin, just enough. Eddington could not watch the sky with his eyes. He had to trust the instrument, expose one plate after another, and hope that somewhere behind the gauze a few stars had burned through onto the glass. He exposed 16 plates during totality. Most showed nothing useful, their starlight smeared into nothing by the lingering cloud. But a small handful held something real. Faint points of light beside a black sun, in the middle of an African afternoon, turned briefly to night. He developed those plates on the island himself, by hand in the tropical heat across the following nights. The work was slow. The stakes were almost unbearable. On one usable plate, he measured the positions of the stars crowded near the darkened sun and compared them with where those same stars sat months earlier, when their light had crossed empty space untouched by any nearby mass. The stars had moved. Not the stars themselves, of course. Their apparent positions had shifted outward, away from the sun, exactly as though their light had been bent on its way past. The question was no longer whether starlight curved. The question had narrowed to a single number: by how much? Far across the Atlantic, on the very same day, the second team fared better. Andrew Crommelin and Charles Davidson, watching from Sobral in Brazil, observed the eclipse beneath a clearer sky. Their main instrument betrayed them anyway, the heat warping its mirror and blurring its images into uselessness. But a smaller backup telescope, almost an afterthought, recorded 7 photographic plates carrying the sharpest, cleanest star fields of the entire enterprise. Those 7 plates would bear the weight of the verdict. The geometry of the universe, if such a thing existed, would be written in the faint displacement of a few stars on 7 pieces of developed glass. Consider what was actually being weighed. 3 numbers had been set down in advance, and this is what made the test so merciless. If starlight ignored gravity completely, the deflection would measure 0. If Newton's framework held, treating light as tiny particles falling through a gravitational pull, the deflection would come to roughly 0.875 arcseconds. And if Einstein's corrected equations of 1915 were right, if mass genuinely curved the spacetime through which the light travelled, the deflection would measure 1.75 arcseconds. Exactly twice the Newtonian figure. 2 pictures of reality, separated by a clean factor of 2, waiting to be settled by photographs of stars. An arcsecond is an angle almost too small to imagine. It is a sliver far finer than anything the unaided human eye could ever resolve. A hair of displacement against the enormous black backdrop of the sky. The measurement Eddington and his colleagues attempted was not crude. It was among the most delicate observations anyone had ever tried to wring from the heavens. They were not asking whether a star had moved across the sky. They were asking whether it had trembled by a fraction of a degree. And on that trembling rested the question of whether space itself had shape. The analysis took months. Plates had to be measured, remeasured, corrected for the warping of instruments and the distortions of heat and the imperfections of early photography. But when the numbers finally settled, they did not point to 0, and they did not point to Newton. The Sobral backup plates gave a deflection close to 1.75 arcseconds. The usable Principi plates, despite the cloud, agreed. Starlight grazing the edge of the sun had been bent by very nearly the amount Einstein's geometry demanded, and by roughly twice the amount Newton's gravity could ever permit. The factor of 2 had fallen, decisively, on Einstein's side. This is worth holding still for a moment. A theory built almost entirely from thought, from a man imagining sealed elevators and the strange equivalents of gravity and acceleration, had named a precise number years before anyone could test it. And the sky had returned that number. Not approximately, not in spirit, but in the literal measurable bending of ancient light around a star. On the 6th of November, 1919, the results were presented to a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room understood what it was hearing. Newton's gravity, which had governed the heavens without serious challenge for more than 2 centuries, had been outmeasured by a younger and stranger theory. The universe was not a stage on which objects were pulled by invisible forces. The universe was geometry, and that geometry could be photographed. Within days the news crossed the world. Einstein, until then known mostly to other physicists, became something close to a household name. The man who had bent the light of the stars. There is a quiet detail in this story that makes it even more remarkable. Years earlier, in 1911, before his theory was complete, Einstein had published an answer for the bending of light, and that answer had been wrong. He had predicted only 0.83 arcseconds, almost exactly the Newtonian value. Had the eclipse been observed then, it might have refuted him, but Einstein corrected his own work in 1915, doubling the predicted deflection, and he knew the earlier figure was wrong long before any ship ever left harbour. The theory had grown sharper than its author's first instinct. The geometry had insisted on its own answer, and the confirmation did not end in 1919. Over the following years, through repeated eclipse expeditions stretching to 1928, astronomers measured more than 3,000 star images, each one a fresh interrogation of the same claim. The measurements clustered, again and again, around the same value. Every clear sky told the same story. Starlight bends around mass, by precisely the amount that a curved spacetime requires, and not by the amount a simple force would allow. So the promise had been kept. The sky had bent, on cue, to a number written down in advance. But notice what this confirmation actually established, and what it left untouched. The eclipse had shown that space curves, that the very paths light follows are shaped by the mass they pass. That alone was enough to overturn 2 centuries of physics. Yet the bending of starlight is only the visible half of the story. Space-time is not merely space. It is space and time, woven together, and Einstein's geometry demanded that mass warp the second as deeply as the first. If the sun could bend the path of a passing photon, then it could also bend something far harder to photograph and far stranger to accept. It could bend the flow of time itself, and that consequence, smaller to measure and larger to comprehend, was waiting in a laboratory tower in a quiet corner of Massachusetts for 2 physicists who would catch time slowing down across a distance you could climb in a single flight of stairs. Their names were Robert Pound and Glenn Rebka, and in the closing months of 1959, they were not looking at the sky at all. They were looking up the inside of a tower. The Jefferson Physical Laboratory at Harvard University held a vertical shaft, 22.6 meters from floor to ceiling, roughly the height of a 7-story building. It was an unremarkable structure. Nothing about that column of air suggested it would become one of the most important spaces in the history of physics. Yet within it, 2 men were preparing to catch time in the act of slowing down. To understand what they were testing, you have to first surrender a belief so deep that most people never notice they hold it. Ask anyone what time is, and they will tell you without a moment's hesitation that it is the same everywhere. A second here is a second there. A clock resting on the floor and a clock hanging from the ceiling tick in perfect agreement, and the only thing that could ever separate them is a flaw in their manufacture. This is not some fringe assumption held by the careless. It is the bedrock of ordinary life. It is the silent contract beneath every appointment ever kept and every train ever caught. That belief is wrong. Not slightly wrong, not wrong in some exotic regime far beyond human experience. Wrong here, in this room, in the small distance between your head and your feet, at this very moment. We hold the belief for understandable reasons. Nothing in daily life reveals the error. The gap between a clock at your feet and a clock at your forehead is so unimaginably small that no human sense, and for almost all of history no human instrument, could ever register it. Generations of brilliant and careful people lived and died certain that time was a single universal river, flowing at one steady rate for all of creation. They were not foolish. They were working faithfully from the only evidence their senses could give them. The error was invisible, and an invisible error is the hardest kind of all to correct. Einstein's geometry insisted otherwise. If mass curves space-time, and if space-time is space and time braided together into one fabric, then mass must bend the flow of time as surely as it bends the path of light. The closer you stand to a massive body, the deeper you sit inside its gravitational well, and the more slowly your clock must run. Not because the clock is faulty, not because anything mechanical inside it has changed, but because the very dimension the clock exists to measure has been stretched by the mass beneath it. The prediction was almost insultingly small. Across the 22.6 meters of that Harvard tower, Einstein's equations called for a difference in the rate of time of only about 2 parts in every 1,000 trillion. Write that fraction out in full, and it dissolves into meaninglessness. It is a difference so faint that it makes the width of a single human hair look like the distance between 2 continents. To measure something that delicate, Pound and Rebka needed a clock of almost unthinkable precision. They found one not hanging on a wall, but hidden inside the atom itself. Their clock was light. More precisely, it was a thread of gamma radiation released by atoms of iron-57, a particular variety of iron that emits energy at one exquisitely sharp and stable frequency, 14,400 electron volts of it. An atom emitting this radiation behaves like a tuning fork of extraordinary purity, vibrating at a rate fixed by the laws of nature rather than by the imperfections of any machine. If anything at all happened to that frequency on its journey up the tower, the atoms waiting at the top would notice. They would quietly refuse to absorb light that no longer matched their own precise pitch. Here is the heart of the matter. A particle of light climbing away from the Earth is climbing against gravity, exactly as a thrown ball climbs against gravity, and climbing always costs energy. A ball slows as it rises. Light, however, cannot slow down. Its speed is the one absolute the universe refuses to bend, fixed and unchangeable no matter what. So light pays the toll in a different currency. It does not surrender speed. It surrenders frequency. It reddens. The gamma ray that left the bottom of the tower arrived at the top, very slightly lower in pitch than when it began, drained by the long climb upward against the planet's grip. And frequency, in the end, is simply time, counted. A frequency is nothing more than a number of cycles ticking past in each second, a clock running at the pace of light. To say that the light reddened as it rose is to say, in the very same breath, that the second measured at the top of the tower was not the same length as the second measured at the bottom. The atoms resting on the floor were aging, imperceptibly, a little faster than the atoms near the ceiling. The difference was real. It was waiting only to be caught. Through 1959 and into 1960, Pound and Rebka sent their gamma rays up and down that shaft, again and again, painstakingly subtracting every competing influence, every faint shift of temperature, every small tremor running through the building. When the numbers finally settled, they had measured a frequency shift of roughly 2.5 parts in every 1,000 trillion, give or take a fraction. It matched Einstein's prediction to within 10%. For the first time anywhere, in a laboratory, on a scale a person could walk across, gravity had been caught in the act of bending time. Consider what that means. The effect was not borrowed from a black hole, or a collapsing star, or the unreachable edge of the observable universe. It was measured across the height of a single building, on an ordinary campus, in an ordinary year, by 2 patient men with a clever idea. Time runs slower near the ground than near the rooftop of the very building you may be sitting in right now. Your feet are aging more slowly than your head. The difference, summed across an entire human lifetime, amounts to a few billionths of a second, far too small for any nerve to feel. But it is not zero. And it is not a figure of speech. It is the geometry of spacetime, written quietly into the length of your own body. It would be easy to file this experiment away as a curiosity, a beautiful confirmation with no bearing whatever on the world you actually walk through. That instinct is the second misconception this part of the story must dismantle, and it is, if anything, even more wrong than the first. The slowing of time by gravity is not an abstraction sealed inside a physics journal, not a number for specialists, not a footnote to a theory. It is running, silently and continuously, inside a device almost certainly within arm's reach of you at this exact moment. Lift your attention, in your mind's eye, past the rooftop of that building, past the clouds, past the highest aircraft, up to a shell of satellites circling the planet roughly 20,000 kilometers overhead. There are dozens of them, sweeping around the Earth at something near 14,000 kilometers per hour, and between them they hold the entire modern world to its appointments. They guide the ship and the airliner. They steer the delivery truck through an unfamiliar town. They place the small blue dot at the center of the map glowing in your hand. Every one of them carries an atomic clock of staggering accuracy, and every one of those clocks is caught in precisely the situation Pound and Rebka studied in their tower, only turned upside down. For these satellites do not sit at the bottom of the gravitational well. They ride near its rim. 20,000 kilometers up, the Earth's mass curves spacetime far more gently than it does at the surface, and a clock in that shallower curvature runs not slower but faster than the clocks we keep on the ground. The very same physics that dragged on the gamma ray climbing the Harvard shaft now lifts the satellite's clock ahead of ours, second by second, day after day. The effect that was almost too faint to detect across 22 meters becomes, across 20,000 kilometers, impossible to ignore. There is a second force tugging the other way, and the tension between the two is where this story sharpens. The satellites are not merely high, they are also moving, and moving very quickly, and motion, by a separate rule Einstein had laid down a decade before his theory of gravity was complete, slows a clock down rather than speeding it up. So each satellite holds two competing corrections inside it at once. The weaker gravity of its great altitude pushes its clock to run fast. Its tremendous orbital speed drags that same clock to run slow. The world's entire navigation system depends on what happens when those two effects are added together. And the answer is not a clean cancellation. The answer is a number, small and stubborn and growing with every passing day, that nobody designing these systems could afford to round away. Work the arithmetic the way those engineers were forced to. The great altitude of the orbit, where the curvature of space-time is gentler than it is down here at the surface, pushes each satellite's clock forward by roughly 45 millionths of a second every day. The relentless orbital speed, 14,000 kilometers per hour of unending motion, drags that very same clock backward by roughly 7 millionths of a second every day. Subtract the one effect from the other, and you do not arrive at a clean and convenient zero. You arrive at 38 millionths of a second, gained by every satellite, every single day, for as long as it remains in the sky. The two corrections do not erase each other, they leave a residue, and the residue is real. 38 millionths of a second sounds like a quantity beneath any possible human concern. It is a span so brief that no nervous system could ever register its passing. A single blink of your eye lasts something on the order of 10,000 times longer than that. You could not feel it, measure it, or even imagine it with your unaided senses. And this is precisely where intuition fails completely. The danger of 38 microseconds is not that it is large. The danger is that it belongs to light, and light is the messenger the entire system depends upon. Light does not blink. Light moves at very nearly 300,000 kilometers in a single second, and the whole quiet trick of satellite navigation is the measurement of how long a radio signal takes to fall from orbit down to the small receiver resting in your hand. The device does not see the satellite. It listens to a timestamp and asks one question: how long did this whisper take to reach me? From that interval, multiplied by the speed of light, it reconstructs a distance. A clock that runs wrong by 38 millionths of a second therefore describes a distance that is wrong by far more than the length of a city street. The error is not in the hardware, the error is woven into the passage of time itself. Consider what this means across a single ordinary day. The mistake does not appear once and then politely hold still. It accumulates. It compounds. Each hour stacks its small dishonesty upon the hour before. By the time a single day has turned, the position your phone believes it occupies would have wandered away from the truth by roughly 10 kilometers. Not 10 meters, which you might forgive. Roughly 10 kilometers, which would place you in the wrong town. The blue dot that you trust without a second thought would drift across rivers and across highways, confidently certain and completely lost. And it would do this not because the engineers were careless, but because the universe keeps two different kinds of time at two different heights. Here is the part that ought to stop you where you sit. Every functioning satellite navigation system on Earth carries the correction for this inside it, deliberately and permanently. The atomic clocks aboard those satellites are tuned, before they ever launch, to tick at a rate that is intentionally wrong by the standards of the ground, so that once they reach orbit and time begins to flow faster around them, they will read correctly to us below. Engineers build the relativity in on purpose. They do not approximate it. They do not round it away. The slowing of time by gravity is not a curiosity confined to a tower at Harvard or an eclipse over the ocean. It is a routine engineering specification, accounted for in the design documents of machines that billions of people lean upon, without ever knowing the reason. This is the moment to dismantle a belief you have almost certainly carried your entire life without once questioning it. Ask anyone what a second is, and they will tell you, with total confidence, that a second is a second. It is the same here as it is there. It is the same for you as it is for everyone. Time, they will say, is the one steady thing, the great impartial river that carries all of us along at exactly the same speed, indifferent and universal and absolute. That confident answer is wrong. Not slightly wrong. Not wrong only at the speeds of starships or near the edges of black holes. Wrong here, in this room, at this height, in the ordinary distance between your head and your feet. The misconception feels unshakable because nothing in daily life contradicts it. Two friends part in the morning and meet again at night, and their watches agree, and so the river of time seems to flow as one. But the watches do not truly agree. They differ by an amount so staggeringly small that no human instrument in a kitchen could ever resolve it. The friend who spent the day on the upper floor of a building, slightly farther from the center of the Earth, and therefore in slightly gentler curvature, aged by an almost unimaginably tiny fraction, more than the friend who spent the day in the basement. Time did not pass equally for them. It only appeared to, because the difference hides far below the threshold of anything they could feel. So time is not a single universal river at all. It is a landscape. It runs faster on the mountain and slower in the valley. It runs faster in your skull than in your souls, by a margin too fine to notice and too real to deny. The bending of space-time by mass is not only a bending of space, the dimension the rubber sheet pretends to show you. It is a bending of duration, of the rate at which existence itself unfolds. And this is the deeper truth the elevator and the tower were always pointing toward. Gravity does not merely pull objects through space. Gravity reshapes the flow of time, and it does so everywhere continuously, including in the few cubic feet of curved space-time that you are sitting inside right now. The honest weight of this lands slowly. We tend to imagine that the strangeness of physics lives somewhere far away, out among the colliding stars, sealed safely behind a frontier we will never personally cross. But the satellites overhead are correcting for time dilation while you breathe. The clock in your wristwatch and the clock in orbit have already diverged. The difference between the rate of your aging and the rate of a pilot at altitude is not a thought experiment. It is a measured, funded, engineered fact, confirmed when physicists flew atomic clocks aboard ordinary airliners and watched them return home disagreeing with the clocks that had stayed on the ground, exactly as the equations had promised they would. And once you accept that gravity bends time even in a place as mild as this, a quiet and unsettling question begins to form at the edge of the mind. If the gentle curvature of the Earth is enough to gain 38 millionths of a second a day, enough to derail a global system within hours of neglect, then what happens where the curvature is not gentle? What happens near a mass so concentrated that the warping of time is no longer measured in millionths, but in halves, in thirds, in the slowing of a clock toward a standstill? The Earth is among the mildest gravitational landscapes the cosmos contains. It is a low and rolling hill. The universe builds mountains. This is the turn the whole story has been leaning toward. The slowing of time is not the strange exception. It is the ordinary rule, written into every height and every depth, and the Earth merely whispers it. To hear the rule shouted, You have to leave the gentle places and approach the violent ones, the spinning worlds and the collapsed stars, and the regions where space-time does not simply bend, but is dragged bodily around in circles. What we have measured here, in towers and in orbit, is the faintest possible edge of a phenomenon, whose full magnitude we have only begun to reach toward with instruments delicate enough to feel it. The fabric does not only sag beneath mass, it twists, it is carried, it moves, and the most perfectly made objects human hands have ever shaped were built and launched for the single purpose of catching that motion in the act. Those objects had a name, and a patience built into them across decades. They flew aboard a spacecraft called Gravity Probe B, lifted into a polar orbit in the year 2004, circling the Earth at an altitude of 642 kilometers. At the heart of that spacecraft spun 4 small spheres of fused quartz, each one wrapped in a film of the metal niobium, so thin it was almost not there at all. They were gyroscopes. A spinning object resists any change to the direction of its spin, holding its axis fixed while the world turns around it, and that single stubborn property was the entire instrument. The spheres were set spinning in the cold and the dark, and then they were simply watched. Their only task was to hold their orientation steady while the spacecraft fell endlessly around the planet, and to report, with a kind of inhuman honesty, whether anything had tilted them. To grasp why such an object had to be built, you first have to grasp how nearly impossible it is to build. These were not merely smooth. They were not round in the way a ball bearing is round, or a marble, or a pearl polished by the sea. They were the most perfectly spherical objects ever shaped by human hands, ground and figured until their surfaces departed from a true sphere by no more than the width of 40 atoms. Consider what this means. If you could swell one of those quartz spheres until it was the size of the Earth itself, the tallest mountain on its entire surface, and the deepest trench in its widest ocean, would rise and fall by no more than the height of a single standing person. The whole planet, smoothed to a marble. That degree of perfection was not vanity. It was the only way to ask the question the mission was sent to ask. The question was whether space-time, the invisible fabric we have been describing this entire time, would reach up and turn those spheres, not push them, not strike them, turn them, slowly, by following the contour of the geometry around the Earth. Einstein's equations made 2 separate and very small predictions about what the gyroscopes would do over the course of a year. The first prediction concerned the simple curvature of space around a massive body, the sagging of the fabric beneath the planet's weight. As Gravity Probe B carried its spinning spheres around and around through that gently warped region, their axes should drift, very gradually, in the plane of the orbit. This is the geodetic effect, the direct fingerprint of mass, curving the space immediately around it. The spheres were not meant to detect a tug, they were meant to detect a tilt, written into them by the shape of the emptiness they moved through. To appreciate how delicate this truly is, consider the unit the scientists were forced to use. A full circle is divided into 360 degrees. Each degree splits into 60 smaller pieces called arc minutes, and each arc minute splits again into 60 arc seconds, so that a single arc second is 1/3600th of 1 degree, an angle already far too small for the human eye to register. A milliarc second is 1,000th of that arc second again. The geodetic drift the mission was sent to measure amounted to only a few arc seconds across an entire year of orbiting. Picture holding up a small coin against the open sky from a distance of 3 or 4 kilometers, and trying to measure the angle that coin covers. That is roughly the size of the larger effect. The smaller one, still to come, was a thing perhaps 170 times fainter than that. This is why the spheres had to be smoothed to within 40 atoms. Any imperfection, any wobble of their own, would have drowned the whisper they were built to hear. When the data finally came back, after years of the spheres turning silently in orbit, the geodetic drift measured negative 6,600 and 1.8 milliseconds per year, give or take 18.3. Einstein's field equations, written down in 1915 by a man who never saw a satellite and never imagined niobium-coated quartz falling through the sky, had predicted negative 6,600 and 6.1. The two numbers agreed to within 0.2%. The geometry held. The curvature of space around the Earth was not a chalkboard abstraction or a clever way of bookkeeping the old force. It was a measurable tilt, impressed into a physical object, exactly where a century-old equation said it would be impressed, and almost exactly by the amount it said. This distinction matters enormously, because it closes a door that intuition keeps trying to leave open. There is a comfortable way to hear everything that has come before. You can tell yourself that space-time curvature is simply a vivid description, a poetic restatement of forces that Newton already understood well enough. The gyroscopes refuse you that comfort. Nothing pulled on them. No string, no field reaching out to grip them. They drifted because the space they occupied was genuinely shaped, and a spinning thing carried through shaped space comes out pointing somewhere new. The fabric is not a metaphor for the force. The fabric is what is actually there, and the force was the metaphor all along. That was the first prediction, the larger and louder one. The second was stranger, and far quieter, and it is the reason the entire mission demanded such absurd perfection. Einstein's equations did not only say that a massive body curves the space around it, they said that a massive body which is also turning will drag the space around with it as it spins. The Earth is not a still weight resting on the fabric. The Earth rotates, once a day, every day, and according to general relativity that rotation grips the surrounding space-time and winds it slowly around, the way a spoon turning in a thick jar of honey pulls the honey into a lazy spiral. The effect is called frame dragging. It predicts that the gyroscopes should drift not only forward in the plane of their orbit, but sideways, perpendicular to it, twisted by the slow rotation of the geometry itself. Frame dragging is not an analogy, and it is not a figure of speech meant to make a hard idea easier to swallow. It is the literal claim that the rotation of a heavy object reaches into the structure of space and time and turns it. Everything around you, the air, the floor beneath you, the still room you are lying in, is being carried in a faint and ceaseless rotation, dragged a fraction of a degree out of true by the planet turning under your back. You cannot feel it. Nothing in ordinary life could ever reveal it. The mathematics become even more remarkable when you realize the size of the thing being claimed. The frame dragging the equations predicted for the Earth was negative 39.2 milliarseconds per year. Not 39 degrees. Not 39 arcseconds. 39 thousandths of one arcsecond. Across an entire year, an angle so small that to measure it at all, you must first remove from your instrument every other source of error, down to the width of a few dozen atoms. And the gyroscopes caught it. After the geodetic drift had been accounted for and stripped away, what remained in the data was a sideways twist of negative 37.2 milliarseconds per year, with an uncertainty of 7.2. Sitting squarely on top of the predicted 39.2. The honey was turning. The fabric of space around our quiet, ordinary planet was being wound slowly into a spiral by nothing more exotic than the fact that the Earth goes around once a day, and 4 flawless spheres of quartz, falling through the dark above the poles, had felt it happen and written it down. This is the moment to remember the sentence we keep returning to. The one John Archibald Wheeler used to compress the whole of the theory into a single breath. Matter tells space-time how to curve, and curved space-time tells matter how to move. We have heard it as a description of bending, of sagging, of the straight path through a warped geometry. Here it deepens. Space-time is not only bent by matter, it is grabbed by matter, set turning by matter, made to participate. The fabric is not the still stage on which the planet performs. The fabric is itself in motion, twisted and carried and alive to every rotation, every mass, every spin. It does not merely register what the Earth does. It is dragged into the doing. Now hold that thought, and hold the scale of it. Everything Gravity Probe B measured, both the curving and the dragging, it measured here, in the company of the gentlest large body within reach. The Earth is a small world, turning slowly, holding the very mildest grip on the fabric that any planet can. The geodetic tilt was a few arcseconds a year. The frame dragging was a handful of thousandths of an arcsecond a year. These are the loudest signals our most perfect instruments could ring from the most placid laboratory available to us. And they are still almost nothing at all. They are the faintest stirring of a phenomenon that, somewhere out there, does not stir but roars. To measure the Earth's twist, we needed spheres smoothed to 40 atoms and years of falling silence. The universe contains objects beside which the Earth's entire grip on spacetime is less than a single grain of sand laid against a mountain range. Objects where the dragging is not a whisper but a torrent, where the geometry does not lean, but folds back on itself entirely. We have felt the edge of the rule. The body of it lies elsewhere, in the places where matter has been crushed past every limit the gentle world ever taught us to expect. Consider what waits at the end of a heavy star's life. When a star many times the mass of our Sun finally exhausts the fuel burning at its core, the outward pressure that held it open for millions of years vanishes in a single instant, and the core falls inward upon itself. What remains, if the collapse halts just short of total ruin, is a neutron star, the densest visible object the cosmos will permit to exist. Into a sphere whose radius measures only 9 to 15 kilometers, barely the width of a sleeping city, it folds something between 1.4 and roughly 2.5 times the entire mass of our Sun. A single spoonful of that material would weigh as much as a mountain range. This is not compression in any sense your hands have ever known. It is matter pressed until the empty space inside the atoms themselves is wrung out and gone, and the geometry responds in kind. The curvature of spacetime at the surface of a neutron star is not twice what it is at the surface of our Sun. Not 1,000 times, not 1,000,000 times, not 1,000,000,000 times. It is 100 trillion times greater, a number so far beyond ordinary experience that the word greater begins to lose its footing. Consider what this means. The same fabric that the Earth tilts by a few arcseconds across an entire year, the same fabric that the Sun bends just enough to nudge a beam of starlight by 1 3/4 arcseconds. A neutron star folds almost to the breaking point. Its physical radius is only about 3 times the radius at which it would vanish entirely behind its own horizon. It rests, every second of its long existence, on the very lip of becoming a black hole. These objects are patient in a way that mocks the human span. They will go on holding the fabric in that ferocious grip long after the last ordinary star has burned out, long after the galaxies have drifted past one another into separate darknesses. The geometry they carve does not relax. It does not forget. It simply persists, a permanent scar pressed into the structure of the universe by a single dying moment of collapse. We are accustomed to thinking of stone as the lasting thing, and motion as the fleeting thing. Here that intuition fails completely. The curvature is the lasting thing. The matter is only the signature that wrote it. To feel how strange this truly is, return for a moment to your own body. You believe gravity is pulling you down. It is not. You are coasting. Left to itself, your body follows the straightest possible path through the space-time around the Earth, the same way the planet itself, swinging through its yearly ellipse, is tracing not a curve forced upon it, but the straightest line available in a region that has been gently bent. In flat space those paths would run forever outward and never return. Near the Earth they close into orbits and gentle falls. Near a neutron star, the straightest available paths begin to wind inward, tightening, and near a black hole they do something the mild world never prepared us to imagine. They lead only in. Every direction that was once an escape becomes a direction that points toward the center. This is the meaning of an event horizon. It is not a wall. It is not a surface made of anything. It is the boundary where the curvature has grown so severe that the speed required to escape exceeds the speed of light itself. Beyond that boundary, nothing that travels at or below light speed can ever climb back out, and nothing travels faster than light. So nothing returns. Not matter, not signal, not the faintest glimmer of warning. The horizon is simply the place where the geometry is tilted so far that the future itself points inward, where moving forward in time and moving toward the center become the same motion. To cross it is not to enter a region you might leave with enough power. It is to have the very meaning of leaving erased from the map of where you can go. And at the heart of it, the equations point to something that breaks the mind to consider. They point to a singularity, a place where the density is not enormous but infinite, where the volume is not tiny but zero, where the curvature of space-time does not reach some staggering 100 trillion times the sun and stop, but climbs without any limit at all. Every quantity that physics knows how to measure runs off the edge of meaning at that single point. The smooth, reliable geometry that bends starlight and slows clocks and drags the fabric around a spinning world arrives there and simply tears. This is not a distant abstraction. The mathematics that has passed every test we have ever devised, the mathematics confirmed by eclipse expeditions and atomic clocks and gyroscopes round to 40 atoms, insists that these points exist, hidden inside the darkest objects the universe contains. Here is the problem. At that point of infinite curvature, the most successful theory of the large scale ever written collides with the most successful theory of the small scale ever written, and the two cannot both be true. General relativity describes the vast and the smooth, the orbits and the horizons and the bending of light across millions of years. Quantum mechanics describes the tiny and the granular, the trembling uncertainty at the heart of every atom. Each has been tested to extraordinary precision. Each has never once been caught in error within its own domain. And yet at the singularity, where the vast has been crushed down into the tiny, both theories must speak at once, and when they do, they contradict one another completely. The equations return not an answer, but a refusal. They hand back infinities, the mathematical sound of a description that is broken in our hands. This distinction matters enormously, because it tells us something humbling about the whole magnificent edifice we have spent this entire journey admiring. The bending of space-time, the warping of time, the dragging of the fabric, the rule that matter tells geometry how to curve and geometry tells matter how to move. All of it, however perfectly it has been verified, is not the final word. It is a description that works flawlessly until the moment it is pushed to its absolute extreme, and there, at the deepest center of the deepest objects, it confesses that it does not know what comes next. The honest answer is that nobody knows. Somewhere inside the geometry we have measured so exquisitely lies a place our finest theories cannot follow, a place where our understanding of curvature itself remains visibly, admittedly incomplete. So we are left holding two truths at once. We have measured the bending of space-time in the tilt of a gyroscope and the redshift of a gamma ray, with an accuracy that would have seemed like sorcery to the men who first wrote the equations. And we have learned, in the same breath, that the very rule we measured so precisely conceals within itself a door we cannot open, a region where the fabric does not merely fold, but ends. The gentle world taught us that every place has a flaw, that you can always fall no further. The geometry of the crushed objects teaches the opposite. There is no flaw. There is only deeper and deeper, and a point past which the words themselves give out. We have traced the rule from a satellite ticking 38 microseconds out of step, through a tower at Harvard, across an eclipse on a clouded island, and into the silent twist of space-time around a spinning planet. Each step took us to a place where the bending was a little stronger, a little stranger, a little harder for the mild world to believe. But the strongest curvature of all does not lie in any of the experiments we have built. It lies far out in the dark, in the moments when matter was crushed past every limit, and in the waves and shadows those moments left behind for us to find. Those waves had been travelling for a very long time before they reached us. Not for years, not for centuries, not for the whole span of recorded human history. The ripples that washed silently over the earth on a morning in September 2015 had been crossing the emptiness for roughly 1.4 billion years. They were set loose by a catastrophe so violent that the words we use for violence feel small beside it, and they left their birthplace when the only life on this planet was single cells drifting in shallow water. There were no eyes then. There was no one to feel the fabric of space stretch and relax as the wave passed. The wave did not care. It simply travelled and travelled and kept travelling for an interval longer than the age of every mountain you have ever seen. To understand what made it, you have to imagine two black holes circling one another in the dark. One held roughly 36 times the mass of our Sun. The other held roughly 29 times the mass of our Sun. They were not gentle objects. Each was a region where space-time had folded so steeply that not even light could climb back out, and they had been spiraling toward each other for ages, drawing closer with every orbit, swinging faster as the distance shrank. In the final moments they were whirling around one another hundreds of times each second, two collapsed worlds moving at a sizable fraction of the speed of light. Then they touched. Then they became one. Here is the part the gentle world cannot hold in its hand. When those two black holes merged, the new object that formed weighed about 62 times the mass of the Sun. But 36 and 29 do not add to 62. They add to 65. 3 solar masses had simply vanished. Not crushed smaller, not hidden inside, gone, converted entirely into the energy of bending space, poured out into the universe as gravitational waves in roughly 0.2 of a second. 3 times the entire mass of our Sun, the mass that warms our world and holds every planet in its grip, was transformed in less time than it takes to blink, into ripples in the geometry of reality. Consider what that release of energy actually was. For that fraction of a second, the merging black holes radiated more power than every star in the entire observable universe shining at once. Not more than our Sun, not more than our galaxy, not more than 1,000,000 galaxies, more than all of them together, every star in every galaxy that our telescopes can see, their combined light outdone by a burst of pure warped space lasting 1/5 of a single second. The number that describes that power has 50 digits in front of the decimal. The mind cannot truly receive a number like that. It can only stand near it and feel the cold draft coming off it. And the strangest thing of all is that this unimaginable outpouring made no light. It made no sound. It released nothing you could see or hear. It made only silence moving through the shape of space itself. By the time that silence reached the Earth, it had spread thin across more than 1 billion light years, and almost nothing of it was left. This is why no one had ever caught it before. The waves were real, but they were faint past all ordinary meaning. To feel one, you would need an instrument that could measure a change in length smaller than anything humanity had ever measured. Far smaller. So we built one, in Hanford, in the state of Washington, and again in Livingston, in the state of Louisiana, separated by some 3,002 kilometers of American ground. Engineers and physicists had assembled 2 of the most sensitive machines ever made. Each one was an L of 2 arms, each arm 4 kilometers long, with laser light running up and down them, watching for the faintest stretch or squeeze of the distance between mirrors, hung in near-perfect stillness. The idea was almost unbearable in its ambition. A gravitational wave, passing through the Earth, would lengthen one arm by a hair while shortening the other, and the lasers would notice. The question was only whether anything in the universe could ever wring those arms hard enough to be heard above the trembling of the world. The answer arrived at 50 minutes and 45 seconds past 9 in the morning, Coordinated Universal Time, on the 14th of September, 2015. First the detector in Louisiana felt it, then, about 7,000ths of a second later, exactly the delay you would expect for a wave sweeping across the planet at the speed of light, the detector in Washington felt the same thing. The signal lasted about 0.2 of a second. It rose in pitch as it went, sweeping upward from around 35 cycles per second to roughly 250. a rising tone that scientists would later call a chirp, the sound of two black holes spiraling into one, written into the stretching of space and read back out by two machines half a continent apart. After 100 years of waiting, the universe had finally spoken in the language Einstein said it would. Consider how long that wait had been. In 1916, only 1 year after he completed general relativity, Albert Einstein worked through his own equations and found that they predicted ripples in spacetime, waves that should spread outward whenever great masses accelerate. Yet he did not celebrate. He suspected the waves would be so faint that no instrument could ever detect them, and for years he was not even sure they were physically real, rather than a kind of mathematical ghost living only inside the algebra. He doubted his own discovery. He thought the universe had hidden this prediction behind a wall of weakness that human hands would never breach. It took 99 years to prove him both right and wrong at once. Right that the waves exist, wrong that we could never feel them. Now stand close to just how faint the signal truly was. As the wave passed through those 4-kilometer arms, it stretched and compressed them by a distance equal to 1 part in a number with 21 zeros. To make that real, hold this in your mind. The change in length the detector measured was smaller than 1/10,000th the width of a single proton, one of the tiny particles inside the nucleus of one atom. The machine sensed space itself shift by less than a fraction of the width of a piece of a single atom, across arms longer than 30 football fields laid end to end. It is, almost certainly, the most precise measurement that human beings have ever made of anything. We built a ruler delicate enough to feel the trembling of the cosmos, and the first thing it felt was the death cry of two black holes from before the age of complex life. The discovery was not announced at once. The signal was so extraordinary, and the consequences so enormous, that the teams spent months testing it, attacking it, trying with every method they had to prove it false. Only when they could not break it did they tell the world. On the 11th of February, 2016, they stood before the cameras and said the words plainly. Gravitational waves had been detected. Einstein's century-old prediction, the one he himself had nearly given up on, was now a measured fact. A new sense had opened for our species. For all of history we had studied the universe with light, with the glow of stars and the colours hidden inside that glow. Now, for the first time, we could feel it. We could feel the shudder of space when massive things collide in the dark, where no light escapes. And here is where a small warmth slips into the cold. For a moment, hold the strange comfort of it. Two black holes, more than 1 billion light-years away, collapsed into one before anything on Earth could think. And the only message they ever sent was a tremor in the shape of space too small to imagine. Across all that distance and all that time, the tremor survived. It reached a planet that had since grown oceans and forests and minds patient enough and humble enough to build a machine that could feel it. The universe is indifferent. The universe did not aim that wave at us. Yet the wave arrived, and we were ready, and for 0.2 of a second the bending of distant space and the attention of human beings touched across 1.4 billion years. That is not nothing. In a cosmos this vast and this uncaring, it may be one of the most improbable handshakes that has ever happened. But the comfort does not last, and it is not meant to. Because feeling the waves taught us only what the curvature does at a distance, in the moment of catastrophe, as it ripples outward and fades. It did not show us the thing itself. It did not let us look directly at the place where space-time folds so steeply that light lies down and cannot rise. The waves were the echo. They were the sound of the door slamming, carried to us across 1 billion years of dark. We had heard the universe at last, and the hearing was a triumph beyond anything our instruments had done before. Yet a question remained, older and heavier than the triumph, waiting just past the edge of the celebration. We had felt the shape of the catastrophe and the trembling of our mirrors. We had not yet seen its face. And the universe, it turned out, was about to let us look straight into the shadow. On the 10th of April in the year 2019, a collaboration of astronomers working under the name the Event Horizon Telescope, released something that Albert Einstein himself never believed humanity would ever hold in its hands. It was a photograph, not a diagram drawn on a chalkboard, not an artist's impression painted to suggest what such a thing might resemble, not a simulation generated inside a computer. It was an actual image, assembled from real light that had travelled across an almost unthinkable gulf of space and time to reach our instruments. And what it showed was a black hole. The black hole has a name. We call it M87 star, and it sits at the very centre of a galaxy named Messier 87, a vast island of stars roughly 55 million light-years away from the room where you are resting now. Think about what that distance means. The light captured in that photograph left its source 55 million years ago. It began its journey toward us before our earliest human ancestors existed, before the continents had settled into their present shapes. It crossed the dark for 55 million years, and at the end of that crossing, it fell into a telescope built by a species that had only just learned how to look. This was no ordinary black hole. Its mass is approximately 6.5 billion times the mass of our Sun. Not 6.5 million, not 6,500 suns gathered together. 6.5 billion suns, all of their matter collapsed into a single object whose gravity is so total that it has carved a permanent wound into the fabric of space-time. To appreciate how vast this single object truly is, consider its event horizon, the boundary from which nothing returns. That horizon spans roughly 40 billion kilometers across. If you placed this black hole where our Sun sits, its boundary would stretch roughly 2.5 times the full width of Neptune's orbit, swallowing every planet in our solar system and most of the empty space between them as well. Yet the photograph did not show the black hole itself. It cannot. This is the strange and beautiful truth at the heart of the image. A black hole is, by its very nature, the one thing in the universe that can never be seen directly. Not because it is too far away, not because it is too small, but because it is defined as the place from which no light can ever escape. What the telescope captured instead was a shadow, a perfect circle of absolute darkness, ringed by a glowing crescent of superheated matter spiraling inward toward oblivion. The darkness was the silhouette of the event horizon, printed against the brilliance of everything falling in. Consider what that darkness truly is. The event horizon is the spherical boundary where the curvature of space-time becomes so steep that the escape velocity, the speed required to break free, finally reaches the speed of light itself. Below that boundary, even light, the fastest thing that exists, the universal speed limit woven into the structure of reality, no longer travels fast enough to climb back out. It is not slowed. It is not trapped behind a wall. The geometry itself has simply tilted so completely that every possible path forward leads deeper in. For a black hole of this size, that radius reaches approximately 19 billion kilometers. A photon crossing that line falls inward, like everything else, toward a destination that none of our equations can fully describe. This is the most extreme curvature that human beings have ever observed. It is also the very same curvature, the very same physical phenomenon that began this entire journey. The same space-time that Isaac Newton could describe but never explain. The same fabric whose bending Arthur Eddington photographed in the gentle deflection of starlight around the eclipsed sun. The same warping of time that Robert Pound and Glenn Rebka measured in a tower at Harvard, where time ran at a different rate across a distance you could walk in 6 steps. The same geometry that LIGO felt trembling in its mirrors as 2 distant black holes spiraled together. All of it, every measurement, every confirmation, every patient decade of work was leading toward this single dark circle. Newton gave us the rules, Einstein gave us the reason, and here, at last, was the reason made visible. The geometry of gravity printed in light for human eyes to see. But look closer at that darkness, and the comfort of understanding begins to dissolve again. Because the event horizon is only the doorway, It is not the destination. Somewhere far inside that boundary, at the very center, our theories predict something they cannot truly handle. A singularity. A point where all the matter of 6.5 billion suns is crushed into a region of zero volume and theoretically infinite density. A place where the curvature of spacetime does not merely become steep, it becomes infinite. And infinity, in physics, is almost never an answer. It is a warning. It is the mathematics telling us that here, at this point, the theory has reached the edge of its own knowledge. This is the tiny hope tempered by a deeper dread. We have learned to see the geometry of gravity directly, to photograph the shadow of the abyss, to feel the ringing of spacetime itself. In doing so, we have arrived at the one place where the very theory that carried us here falls silent. General relativity, the most precisely confirmed description of gravity ever written, the theory that has passed every test for more than a century, becomes fundamentally incompatible with quantum mechanics, the equally successful description of the very small, in exactly these conditions. Inside the singularity, both cannot be true at once. So when you ask what truly happens at the center of M87 star, where spacetime folds infinitely upon itself, the most honest answer that science can give is also the most humbling. Nobody knows. Not yet. Perhaps not for generations. So here we stand at the end of the layers. We have followed the curvature from a falling apple to a falling photon, from a tower in Massachusetts to a galaxy 55 million light-years away. We have watched gravity reveal itself as geometry, as the bending of space and the slowing of time, as a living fabric that ripples and twists and drags and folds. At the deepest point, the fabric closes over a mystery our finest minds cannot yet read. Yet the same geometry that becomes infinite inside that distant shadow is not confined to the centers of black holes. It is not something happening only out there, in the dark 55 million light-years from your bed. It is here. It is the curvature flowing through the room around you, through the floor beneath you, through your own resting body, in this exact and quiet moment. Consider what that truly means as you lie here in the dark. The same geometry that folds infinitely upon itself at the heart of M87 star is the geometry cradling your body against the mattress in this moment. There is no separate physics for the small and the quiet. There is no gentle exception carved out for the ordinary, no softer set of laws reserved for a still room at the end of a long day. The curvature that bends starlight around the sun and slows the ticking of a clock at the bottom of a tower is the very same curvature holding you exactly where you are tonight. Not as a comforting image, not as a figure of speech offered to make the science feel closer, as the literal, measured, verified shape of the reality you are resting inside. You are not a visitor to this geometry. You are made of it, held by it, written into it. Think of the Earth itself, carrying you and everyone you have ever known on its long path around the sun. In ordinary space, that path looks like an ellipse, a curved loop traced again and again across the years, returning each winter to where it began. But in the full 4 dimensions of space-time, with time added as a genuine direction alongside length and width and height, that looping orbit straightens into something almost perfectly straight. The Earth is not being pulled. The Earth is not being held on an invisible leash, reaching across one astronomical unit of emptiness toward the sun. The Earth is simply following the straightest path available to it, through a region of space-time that the sun's mass has gently curved. A world line only about 1 astronomical unit wide in space, yet stretched across light years in the direction of time. The planet falls forever, and the falling feels like a circle, and the circle is really a line, and the line is the truest road through a bent and silent landscape. This was the revelation that took humanity 228 years to reach. Isaac Newton gave us gravity's rules in 1687, in the pages of the Principia, describing the strength of the attraction with a precision that guided ships and predicted comets, and held for centuries without serious challenge. Yet Newton could never say what gravity actually was. He could not explain how it reached across empty space to grip the planets, how one body could pull another it never touched. He called it action at a distance, and he confessed that he could not account for the mechanism, and for more than 2 centuries that confession simply hung there, unanswered. Then, on the 25th of November 1915, Albert Einstein closed the gap. Gravity is not a force reaching across the void. Gravity is the shape of the void itself. The thing we had searched for across 200 years was never a hidden hand. It was the curvature of the stage on which everything stands. The physicist John Archibald Wheeler later compressed the whole of it into a single sentence, and that sentence has followed us through every layer of this journey. Matter tells space-time how to curve, and curved space-time tells matter how to move. Hear it now at the end, and hear how complete it is. Nothing in that sentence is passive. Nothing in it is fixed. Matter and space-time are locked together in perpetual conversation, each instructing the other, neither one the master, and neither one the stage. The fabric is not a thing that gravity happens upon. The fabric is gravity, and you, lying here, are a small concentration of matter quietly telling the space-time around you how to bend, while that bent space-time quietly tells the atoms of your body how to settle and rest. And here, at the very end of our long descent through the layers, a quieter question begins to rise. It is no longer a question about physics. The physics, for all its remaining mystery, has answered a great deal. We know now that time bends, that space curves, that the geometry is real and measurable, that the same truth nudges the clocks aboard distant satellites roughly 38 millionths of a second ahead of your own with each passing day. What rises now is a question physics was never built to settle. It is the question of what all of this means for you. A brief arrangement of matter that has somehow learned to read the shape of the thing that holds it. Perhaps there is something diminishing in everything we have uncovered. Perhaps to learn that you are a knot of mass following a geodesic, obeying the same equations as a falling photon and a collapsing star, is to learn that you are smaller and less special than you imagined. Perhaps the universe is precisely as indifferent as it appears, a vast and patient geometry that curves the same way around a sleeping child as it does around the dead remnant of a sun, caring nothing for the difference. Or perhaps the opposite is the truer reading. Perhaps the most astonishing fact in this entire story is not that space-time curves, but that a portion of that curved space-time woke up, looked around, and worked out the rule. Not because the universe required witnesses, it did not, but because, against odds we cannot yet calculate, the geometry folded itself into something that could understand its own folding. That is the strangeness no equation removes. The cosmos did not need to be comprehensible. There is no law demanding that the bending of starlight be the sort of thing a mind could ever measure. No principle insisting that the slowing of time should leave a trail faint enough to follow and clear enough to read. Yet a man in a patent office imagined a falling elevator and reasoned his way to the shape of reality. A team on a clouded island photographed a darkened sun and caught the geometry in the act. 2 detectors a continent apart trembled by less than the width of a proton and heard 2 black holes collide a billion light years away. The universe permitted itself to be known, and whether that is a small thing or the largest thing of all is not a matter that physics can decide for you. These questions have no universal answers. Different people, lying in different rooms under different skies, will reach for different meanings, and none of them will be able to prove the others wrong. One listener will feel the indifference of the geometry as a cold and final verdict. Another will feel that same indifference as a strange release, a permission to matter on a human scale, precisely because the cosmos imposes no meaning of its own. Both are standing on the same curved ground. Both are following the same straightest path through the same bent space-time. The geometry does not choose between them. It only holds them, equally, with the patience it shows to everything, and the holding extends further than any of us can truly picture. Out there, even now, the same law is at work on a scale that empties the words we use to describe it. The light from M87 star left its galaxy 55 million years ago and has been falling through curved spacetime ever since, only now reaching the instruments that drew its shadow. The ripples from two merging black holes crossed 1.33 billion light-years of bent and stretching fabric to arrive as a chirp lasting 0.2 of a second. Across all of that distance, through all of that time, the rule never changed. The geometry that curves around your resting body tonight is the geometry that folds at the center of a galaxy you will never see, governed by the same equations, written in the same silent grammar, indifferent to the difference between a sleeper and a star. And yet, even here, our knowing reaches a wall it cannot pass. For all the geometry has surrendered to us, there remains a place where understanding simply stops. The same description of gravity that maps the cosmos with such unreasonable fidelity refuses to reconcile with the physics of the very small. General relativity and quantum mechanics, the two most successful theories humanity has ever constructed, cannot both be wholly true in the most extreme conditions the universe allows. At the center of a black hole, where the curvature climbs toward the infinite, the two descriptions collide, and neither survives intact. Somewhere inside that contradiction lives everything we still do not know about the fabric of reality. The story is not finished, the deepest layer has not been read, and the honest scientist, asked what waits at the bottom, gives the same answer the universe has always given to those patient enough to keep asking. Not yet. We do not know yet. So you lie here at the edge of the known, held by a geometry that is at once perfectly understood and profoundly unfinished. Beneath you, the floor presses up because space-time tells your falling body to stop. Around you, the room holds its shape because mass everywhere is quietly instructing the fabric, and the fabric is quietly instructing the mass, in a conversation that has run without pause since the first instant of time. You are inside that conversation. You always have been. From the apple that may or may not have fallen in a Lincolnshire garden, to the photon bent around an eclipsed sun, to the clocks drifting apart in orbit overhead, every layer of this long descent has been describing the single quiet fact of where and how you rest tonight. Perhaps that is all gravity ever was. Perhaps the bending of space and the slowing of time are not a puzzle waiting to be solved, but a home waiting to be understood. A shape we were always meant to settle into. Or perhaps the geometry we have mapped is only the surface of something deeper, a language written over a grammar we have not yet learned to read. The two greatest theories humanity has ever constructed, general relativity and quantum mechanics, cannot both be wholly true in the same place at the same moment. Where curvature climbs toward infinity, at the heart of every black hole, both of them fall silent. Nobody knows what speaks in their place. Not because the question is unimportant, but because we have not yet built the language to ask it. These questions carry no settled answers. Different minds will hold them in different ways. Some will find in the unfinished theory a reason to keep searching, a horizon that recedes precisely because it is worth chasing. Others will find in that same incompleteness a quiet permission to rest inside the mystery without demanding that it resolve tonight. Both responses are honest. Both have kept human beings looking upward for as long as there have been human beings to look. No instrument can tell you which one is yours. The choice, like the curvature beneath your body, belongs to you alone. Consider, one final time, the scale of the thing that holds you. The same geometry that presses you gently into the bed tonight reaches outward without a break, curving around every star, twisting around every spinning world. It stretches faintly even now from the collision of two black holes that merged roughly 1.4 billion light-years away, a collision that rippled the fabric of space by a distance smaller than 1/10,000th the width of a single proton. That same fabric drapes itself around a black hole 55 million light-years from here, a shadow nearly 40 billion kilometers wide, where light itself can no longer climb back out of the curve. You are not standing apart from any of this. You are made of the same fabric. You are resting inside the same fabric, instructing it and being instructed by it. without a single moment of pause. And here is the gentlest truth of this entire long descent. To be small inside such a structure is not the same as being insignificant. It took humanity 228 years to travel from Newton's rules to Einstein's reason. It took only a single century more to hear two black holes collide across more than 1 billion light-years of curved space. The story is not closed. The deepest layer is still being read. Somewhere in the gap between the geometry we understand and the geometry we do not, there remains room for discovery, room for wonder, room for whoever comes next to ask the question better than we have yet learnt to ask it. The universe bends. It bends around you. And it has not finished telling you what that means. So close your eyes now, if they are not already closed. The floor still presses up against you. The room still holds its shape around you. The clocks in orbit overhead still drift, microsecond by microsecond.